Okay, so what follows directly from relative atomic mass is average atomic mass. Almost every element has isotopes, and when you look at the periodic table and you see the non-integer value that is in the square, like for instance, carbon has a 12.01 with its 6. This 12.01 is the average atomic mass, and it is taking into account the mass of carbon 12, carbon 13, and carbon 14. And that is called the average atomic mass, which is the weighted average of all isotopes of an element. So we're going to start with some candy bars, okay? I happen to have 6 4-ounce candy bars with me and 9 8-ounce candy bars, and I want the average mass. So some people might say, okay, well, we average 4 and 8, add them up, divide them by 2, and we get 6 ounces. Well, that's not the average mass of these candy bars because we don't have the same number of each bar. There are twice as many, well, no, almost twice as many 8-ounce bars as 4-ounce bars. So we need to take the population or the percent or the fraction, whatever you want to call it, into account when we are doing the average mass of the candy bar. So to do that, we do what's called a weighted average calculation. Believe it or not, you have done weighted average calculations before in algebra and probably quickly forgot them, but this is how one does it. You take the mass of the first isotope times the fraction of that isotope. So it's the percentage divided by 100. Then you take the mass of the second isotope divided by the fraction of that isotope. And if you happen to have 3 isotopes, you would do mass 3 times fraction 3. I've given people problems where there were 5 fractions. But anyway, this basic, mass 1, fraction 1, added to mass 2, fraction 2, gives you the average atomic mass. It's weighted. So what we want to do is the candy bar problem. Okay, so to find the fraction, first we need to find the total number of candy bars. So up here we had 6 of the light ones and 9 of the heavy ones. 6 plus 9 is 15 candy bars. So the fraction of 4-ounce candy bars is 6 divided by 15. The fraction of the 8-ounce candy bars is 9 divided by 15. And somewhere I have a number. 6 divided by 15 is 40%, or 0.4. And 9 divided by 16 is 0.6. Okay, if we wanted a percentage, we would then multiply that times 100, but we don't. So if I want to find the weighted average of the candy bars, I'm going to take the mass of candy bar 1, let's call it 4 ounces, times the fraction of the 4-ounce candy bar, which is 0.4, added to the mass of the second candy bar, which is 8 ounces, times the fraction of that candy bar, which is 0.6. If I add those two together, I get 1.6. That would be ounces plus 4.8 ounces. I hope that's right. And I get a mass of 6.4 ounces for my candy bar. This is the weighted average. This does not equal 6 ounces. It's not a whole lot different, but it is different, and it's important. So let's take a look at what happens if you have an element. So chlorine happens to have 2 isotopes. Okay, so we're looking at the weighted average of chlorine. Chlorine 35, remember 35 is the mass number, and chlorine 37. These are the masses. I rounded off. The mass of chlorine 35 is actually something like 34.99, and this is 36.97. I just rounded. The percentages are true. Chlorine 35 makes up most of chlorine. It's 75.78. Chlorine 37 makes up 24.22% of the rest of the chlorine, or of the total chlorine. You can tell I've been on vacation. So to do the calculation, the first thing we do is take the percentages, divide by 100, and get the fraction. Okay, 0.7578, 0.2422. Then to do the calculation, I take the mass of 1. Doesn't matter which one you pick, just make sure you get the right mass with the right fractions. So the mass of 1 was 35. The fraction of that is 0.7578. Okay, this is in atomic mass units. I'm going to add that to the fraction of chlorine 37, or let's do the mass first, right? Do this in order. 37 AMU times the fraction, which is 0.2422. I found it's usually easiest just to multiply these together to keep track of things. So 35 by times 0.7578 gives you 26.523. I cannot read that number. That might not be 523. Let's just believe it. And I'm adding that to 8.96 AMU, the answer to that multiplication problem, and I get 35.48 AMU. If you add these up and discover this is not a 5, let me know. But that is the average atomic mass, MASS, of chlorine. So that's all we do for weighted averages. It's not that bad.